All right, hello everyone. My name is Jake Schermeyer, and today I'm going to be talking about a new data set that's really created in the SpaceNet style, the same similar framework as SpaceNet. So open licensing, a really expansive data set, very high quality, and the focus of this data set is really going to be on aircraft and aircraft detection in overhead imagery. And it also incorporates something cool, which is a very large synthetic data set generated from one of our partners, AI Reverie. So this paper actually appears in WACV 2021, and it is called RarePlanes Synthetic Data Takes Flight. Want to acknowledge all of my co-authors on this: Thomas Hostler, Adam Van Etten, Daniel Hogan, Ryan Lewis, and Dale Kim. So RarePlanes is now the largest openly available data set built to test the value of synthetic data for machine learning applications from an overhead perspective. It is a unique collaboration between CosmicWorks, which is my research lab that is leading part of this workshop, and we're really focused on that applied geospatial computer vision domain. We partnered, in this case, with a company called AI Reverie, and they focus on generating synthetic data for various computer vision use cases. So why do we do this? Well, previous research has shown that synthetic data can reduce the amount of real training data needed and potentially improve performance for many tasks in the CV domain. So the paper ultimately will go into a few experiments with using the synthetic data, but ultimately this is really a data set first and foremost, and the experiments we're leaving up to future authors. So what is AI Reverie, and why? What is their platform? What makes it unique? Ultimately, they have built a platform to create synthetic data that sits on top of the Unreal Engine, and can really be used to try to increase the quality of your training data and then improve the performance of your models. And really, ultimately, what we're showing in this example here is that these elephants are being mistaken for different types of animals, sheep or cows. However, but when we retrain the model using AI Reverie synthetic data, ultimately that we can improve their model's performance, and now we're able to accurately identify and track these elephants. So when we saw this technology, we thought about what are the applications really in the overhead domain or the overhead perspective, because limited research has really been done in the overhead perspective to test the value of synthetic data. And also, we really wanted to build an excellent benchmark data set for aircraft detection as well. And I'll talk in a little bit here about how our data are annotated really to enable that and enable various tasks beyond just find all of the planes in this image. This is really ultimately what the RarePlanes data set is. It contains real data from Maxar's Worldview 3 sensor. So these are these top two rows here. So we've got our satellite imagery from Worldview 3, as well as our labels here of the aircraft, which are hand annotated. And then the synthetic data here is generated using AI Reverie software. Software is interesting in the sense that it ingests real geospatial imagery and metadata to procedurally generate synthetic 3D environments of real-world locations. So these environments are then loaded into the Unreal Engine, and then synthetic images are automatically generated along with annotations, which are also automatically generated. So the software is really flexible. It enables you to have different biomes or weather conditions. You can tweak the resolution of the data. So particularly the biomes and the weather conditions are particularly interesting, as you can do things like make it snow in Miami or change the backgrounds into dirt or grass based on any real world location. So very customizable. And this means you can generate really large and heterogeneous synthetic data sets that could be great for improving model generalizability. So a general outline, that was our introduction to RarePlanes. So I'm going to talk about the data set as a whole and the label taxonomy. And I'm going to walk us through some of the benchmarks we've already done, a few of the experiments we've conducted, and then ultimately the resources. So you can go out and start playing with this data set today and downloading it for free. It's hosted through the AWS Open Data Program, just like SpaceNet. super permissive licensing. So if you work for a company or you're in an academic institution, anybody can use this. So in terms of our data set overview, looking at this map on the right here, our real airfields are blue dots. Our synthetic airfields are red dots. This is really a large data set even in both domains. In the real world, we have 253 WorldView 3 satellite scenes across 112 locations, 22 countries. And we really created this data set to have a lot of geographic diversity and stratified our areas, our airfields that we selected by different climate zones and biomes to ensure that we had really a robust data set that was representative of global settings, even though most of our airfields are spread across the United States and Europe. We have over 14,000 aircraft labeled here with 10 attributes. I'll talk about what the attributes are in a moment. Over 2,000 square kilometers of total imagery here from Maxar. Our synthetic data set is 50,000 AI Reverie images across 15 locations and over 600,000 aircraft labeled here, again, with those 10 same attributes, over 9,000 square kilometers of simulated area. And again, this is on the S3 through the Open Data Program, and you can download it here at this bucket, RarePlanes-public. Just want to talk a little bit more about our geographic diversity here. As I said, we stratify our airfields and our real data set across many locations and many different biomes and climates. This means you can have a lot of different backgrounds here. It's really difficult to see, particularly in the snow scene where all of the aircraft are. So a challenging task for computer vision that that computer vision would have to overcome. But there are actually some tiny aircraft parked here in the snowy landscape. We also have desert and dirt runways, grass landscapes, various weather conditions, some cloud cover and haze included as well. So again, very large data set that we hope will increase generalizability to different tasks. So when we first built the RarePlanes data set, we really wanted a unique, we really went with a unique data labeling strategy here. We ultimately chose to have a diamond style annotation here. And this diamond style is important as once you're done annotating it, you can actually measure from the first node to the third node and pull out the length of an aircraft, and then measure from the second node to the fourth node in this polygon and pull out the wingspan of the aircraft. And that's very important for being able to discern and tell different types of aircraft apart. So it's really the first step in classifying what an aircraft might be. And on top of that, we also add in various other annotations, like the shape of the wings. So in this case, these two planes here have swept wings. This smaller aircraft here has straight wings. We talk about the wing position, if they're high or low mounted. The class, the FAA class, which is basically which airfields an aircraft can land at. The roller type, is it a commercial aircraft? Is it a large aircraft? Is it small? Is it have some sort of military purpose? Other things like the number of engines, the propulsion type, so jet engines, propeller aircraft, unpowered, and then the number of tail fins here. So these two, the black plane and this other large aircraft that has a single tail fin. The smaller one has two tail fins. All of this is really used for being able to discern and then ultimately declare what type of aircraft this is. So we built this in a very hierarchical fashion. Interestingly enough, a lot of these attributes could be used for zero-shot learning applications. And beyond that, really you can start to combine these together to build your own custom classes. So you provide source code where you're able to ultimately pull out, say, I want to find different aircraft where we have a certain type of propulsion, a certain wing shape, and a certain role. You can build all of that together and then start creating custom classes. And this enables you to create really rare classes that you can then try to boost and augment with synthetic data. Ultimately what we're showing here on the right is just our hierarchy of labels here. So for each plane has that diamond style annotation, the polygon, and then on top of the polygon sit all of these sub attributes and the multiple different choices here that could exist for each of those sub-attributes. So each plane and each airfield in and of itself is a data frame that you can use it and work with. So beyond the diamond annotation style, which we see centrally here, the diamond is really easily convertible to a bounding box, which is nice for various computer vision applications. You could also convert this very easily to an oriented bounding box if that would be of interest as well for other networks. We also provide the full instance segmentations for the synthetic data only. This was not possible for a real data simply because it would have been far too expensive to do so. So I'm going to move into our benchmarking phase here. So we conducted multiple experiments really using this data set, and I'm going to walk us through a few examples here and also discuss some of the motivations for doing this. So some of the basic detection tasks here would be like aircraft roll detection. So here we're using a network called MaskRCNN to be able to detect these different aircraft here and then classify their roles. So if they're a small or medium or large civil aircraft or other types of roles we have in the data set. Simpler tasks like aircraft detection, obviously quite possible here as well. And then we get into starting to build custom classes. So detecting aircraft here, we're using a YOLO style network to do so, and detect aircraft and map their different types of propulsion and the number of engines they possess. So really we're able to successfully pull out even some of these very fine grain attributes for various types of aircraft. And as I said previously, as we build these custom classes out, that allows for increasing levels of complexity as you build more and more diverse and complex classes by adding more and more attributes in. Your task for finding these different types of aircraft becomes more challenging. We also built a tutorial. Our intern over the summer, Ari Chada, built this great tutorial on YOLO using YOLO v5. So he has an AMI, an Amazon machine image, so you can actually spin this up on EC2 and run through this tutorial. He has a really great GitHub here that gets you started on that. If you don't want to use Amazon, we also have a great Docker file already built out, so you can just spin this up and get started. The tutorial itself has multiple steps, really a 4-step process. It runs through in a Jupyter Notebook format, where we do a lot of the pre-processing. Get you started creating custom classes, creating configuration files for how to train your models, and then creating your YOLO style training data. And then ultimately you train your model, post-processing. So we're really stitching your outputs back together. So a key characteristic of geospatial computer vision and machine learning is that the images are so large, so you can't load them all in. So therefore, you typically have to stitch your outputs back together. This shows you a way to do that, so you can have full airfield style predictions in a GeoJSON, so vectorized format that you could load into a GIS. And then ultimately model scoring, so you can quantify and evaluate your performance for how well your model is performing. So this was some of his experimentation, really showing if you start to create custom classes using this data set, how well can you really do for detecting certain types of aircraft. And notably here that typically we find that more training data is better. Certainly here where we have over 2,000 instances, our performance really reaches an F1 score of 0.9 or exceeds it. But interestingly enough, as you have, even just over 100 training data examples here, or 200, 300, that works pretty well. Of note, the single engine jet propulsion aircraft were pretty tricky to find and map. However, the unpowered aircraft usually have a very distinctive shape to them, so it's typically easier for our computer vision algorithms to find them. Impossible for our algorithms to really find these jet propulsion planes with 10 training instances. So some other experiments we did, that was really only using real data, the last experiments I showed. So what if you wanted to replace real data with synthetic data, and how would that go? So we conducted some investigations here really to show that and quantify that. And we did this really with a traditional transfer learning approach, where we first train on our synthetic data for a portion of time, and then we train on our full real data set for another portion of time. And this is really the basis for a lot of synthetic data training pipelines. And we conducted an experiment here really to show that you can actually reduce the amount of real training data you require for these tasks. And when we're looking at our metrics here, mean average precision and mean average precision with a IOU threshold of 0.5. What you can see here is that using just 10% of the real data, so that's going to be our yellow bar here, you can achieve near equivalent performances to using 100% of the real data. So that's pretty powerful, because collecting and annotating real data, particularly satellite imagery, can be very expensive and time-consuming process. And if you're able to just use 10% and achieve near equivalent performance, that's ultimately a really strong and beneficial value proposition for synthetic data. I'll also note that if you train on synthetic data only, this ultimately shows we have quite a significant performance boost, particularly in mean average precision, less so here. We did not explore the value of domain adaptation. I think that would be an excellent use case for research and exploring if domain adaptation could help improve just directly mapping aircraft using only synthetic data or domain adapted synthetic data. Another motivation in this study was really rare object detection. So this is what the rare in RarePlanes comes from. So can we find an object where we have really limited real training data examples? This is a very common problem in Earth observation and remote sensing data, particularly because you cannot guarantee that you will always observe an object of interest when you're collecting your training data, when you're collecting your images, right? So a different use case where here might be, can we use synthetic data to artificially increase the prevalence of that object in our training data set? So say we wanted to find all the Beechcraft starships in the world and monitor where they were. There's only 6 active in the world right now. It's going to be very difficult to find these aircraft typically. RarePlanes does contain several of these aircraft, interestingly enough. But just as an example here, what if you wanted to find these? Could you augment with synthetic data to be able to find them more readily? So looking at this, we built some experiments really to start to understand where real data starts to break down based on the number of training data examples you have here. So looking at this graph here, we trained a network YOLO v3 in this case. Our y-axis here, we have our mean F1 score. Our x-axis, we have our number of real training data examples for each object. And ultimately what we were showing here is that when we have 10 or fewer real training data examples, our performance is terrible, right? And really truly the same for 30 or fewer real training data examples. Then performance gradually increases as you get greater than 300 and starts to plateau here. But can we add in synthetic here, and now can we attempt to boost our performance in these rare classes? We took a slightly different approach here to do this. In this case, we trained on our full rail data set to maximum performance. Then we trained on just some classes of interest that we were interested in boosting our performance in the synthetic data space. And then we train again, going back to our real domain, and train on our real data again for a very short portion of time. Only doing this for about 2 hours of total training. This means you can use less synthetic data, and it can ultimately, we found this technique to be very performant and be able to boost our performances for these rare classes. So looking at this chart again, so the orange bars here are real data only. The green bars are when we do this transfer learning approach I just described, adding in the synthetic data. And ultimately, you can see here that we're able to now successfully detect really rare classes of objects with much better performance. So increasing from about a 0.05 to over 0.3 when we have 10 or fewer real training data examples. Although the performance is not excellent, it's certainly a good starting point and shows that synthetic data could be valuable for really boosting performance in these rare classes. A few resources here that I want to point out. As I said, this is an open data set, so it's licensed as a Creative Commons 4.0 share alike. So that means all you have to do is really attribute the data set. You can use it for any purposes, be them commercial or academic. We have a number of great resources here. So the code base I want to point out first and foremost is you can use our pre-processing pipeline to get started with this, start to build your own custom classes, and work with the data set and be able to transform our geospatial annotations into more standardized computer vision annotations like COCO style format, for example. Additionally, we have some pre-trained algorithms and weights shared here as well to get you started. But again, this is really just a starting point. As data scientists, it will really be up to you to start unpacking and working with this data set more fully to unlock its full value. We have a really detailed user guide and data set information here at this URL, cosmicworks.org/rareplanes. This will provide a lot of additional details that go even beyond what the paper describes in terms of how we annotated the aircraft, what the attributes actually mean, as well as different statistics like the number of different aircraft types, the weather conditions. All of that is really contained and stored and lives here. Finally, I want to point out the RarePlanes data set on S3. So this is stored at this bucket here, RarePlanes-public, and that is made available for free through the AWS Open Data Program. So all you really need is an AWS account, and you're able to go on here and download this full expansive data set for free today. Lastly, I'd like to point out our two organizations and give a shout out to our partners at AI Reverie for providing the great synthetic data that ultimately contributed to this data set. And also, please visit us at cosmicworks.org if you'd like to learn more about our various research projects that are all focused really on that geospatial domain, and learn more about our other initiatives like SpaceNet. So thanks for your attention. Again, my name is Jake Schermeyer. Looking forward to interacting with you all here at WACV virtually.